This is the part 4, or the rest part of chapter 2, which is about process flows. The subchapter 5 is about degree of freedom analysis. Degree of freedom analysis, shortly DOF analysis, is very important thing. Um, Let me think about what we have done from chapter 1 and the previous subchapter of chapter 2. In the very first chapter, you have tried to evaluate the processes um, by using generation consumption analysis. In this process, you have several criteria to evaluate your own processes. The first one is RP ratio or BP ratio in moles. So RP ratio means reactant per product, or BP ratio indicates byproduct per product. Or in atomic economy, you have used the PR ratio. In this case, PR should be counted as mass. The other thing is process economy in dollar. Also, you have designed or synthesized your reaction pathways by using some weight factors for the reactions. Then you have improved your process. Then we have gone to the chapter 2. Then we have calculated some unknown variables from process calculations. In the process calculations, you have used the material balance equations plus some restricts from the problems. So then we are right now on the DOF, degree of freedom analysis. Actually, you have done the degree of freedom analysis already in the previous subchapter 4 for the process calculation. For example, in step A, you have counted the number of material balance equations by defining the component for material balance equations. Then in step B, you have counted the number of unknowns or variables. Then in step C, you have found additional restricts or equations. Then finally, total number of equations, including material balance equations or additional restricts, is equal to the number of unknowns. When those numbers are equal to each other, then I have said we could solve the problem. That is the degree of freedom. Degree of freedom is equal to freedom minus restrict. Freedom is the number of unknown variables or variables, and the restrict is the number of equation plus restricts given to you from the problems. Degree of freedom analysis, RFPED, means for determining if a specific process flow calculation problem is solvable or not, without actually solving the problem and setting up the equation. So I'd like to emphasize that you will do the degree of freedom before calculating the problems. Here is the basic procedure. The first, draw a flow diagram and choose a system. You did it in step A for the process calculation in the previous subchapter 4. Choose component also in the step A. Label the flow diagram to show the components in each stream and any accumulation in the system. Write down any chemical reactions. You did it in step B in the process calculation. Number 4, count the number of independent variables. The variables indicate, sometimes we can call it as unknowns and also freedom. So variables are unknowns or freedoms. So how we can count the number of independent variables? You could classify the variables into two different variable groups. The first one is stream variables, and the other thing is system variables. So how to count the number of independent stream variables? Please count the number of components in each stream, then adding them all up, of course. How to count the number of independent system variables? Count the number of independent chemical reactions plus the number of components that accumulate in the system. What are the system variables? You would have three different stream variables. What is that? The first one is the generation. The other thing is consumption term. The other thing is accumulated terms in systems. So I have said you should count the number of components that accumulate. That is related to the accumulation term. How about the other generation term and the consumption term? I have said chemical reactions. Chemical reactions indicate generation term and consumption terms. Chemical reactions were actually balanced chemical reactions would have the specified stoichiometric coefficient. The stoichiometric coefficient indicates the ratio between generation terms or between consumption terms or between generation and consumption terms. So from the chemical reactions you could obtain the generation term and consumption term. So for counting the number of independent system variables, just count the chemical reaction equations as unknowns, but do not count accumulation terms and consumption terms. You will learn about that from the following examples. You have counted the number of unknowns or variables in the previous slide. Then it's time to count the number of independent equations or independent restricts. The first one would be the basis. The second one is about stream specification. The third one, system specification. The first one is, of course, material balance equations. So the summation of those number of bases, specifications, and material balance equation is the number of independent equations. Let me check the text in the tables. Step A. Count the number of specified flows. Usually, there is only one flow specified that serves as the basis, so it is about the basis. Usually, the basis is given to you, which is only one. B step. Count the number of stream composition specifications. Step C. Count the number of system performance specifications. So again, stream and also system specification. And the first one is, of course, material balance equations. In my strategy, in step C, I have considered the material balance equations first. If there are n components in a system, then there are n material balance equations. We did it in the process calculations. And then let's go to the step 6. Calculate degree of freedom is equal to freedom or number of independent variables or number of independent unknowns minus restrict number of independent equation or restrict or information. So that is the degree of freedom, DOF. If degree of freedom is equal to 0, that's what I want. The problem has an equal number of variables and equations, and therefore there is probably a solution. So the problem is totally specified exactly. So we can solve the problem. But if degree of freedom is less than 0, the problem is overspecified. There are more equations than variables. There are more specifications than unknowns. Some of the equations are either redundant or repeated or inconsistent. So again, some of equations would be the same. So you should not count one of them. Or sometimes they are inconsistent. So in that case, your problem is problematic, some problems, or bad problem. If degree of freedom is larger than 0, problem is under-specified. Again, under-specified. It means we have too many freedom. We need to have more restrict. We can make the restrict. There are more variables or unknowns than restrict or equations. This is an opportunity for optimization. You can add more equations or you can add more conditions that might describe desired outcomes, such as a minimal cost or something. So you should add more information into the problem. Here are two examples to clarify whether equations are independent or not. So I should emphasize the word independent for the unknowns and for the equations or restrict. If a reactant is completely consumed, so A as the reactant is introduced into the system, into this system, and this is the reactor. We have one reaction like A to B, and uh, we can assume that this A is completely converted to B. So maybe we could write down only B for the output stream. Of course, in the general cases or practical cases, we should have B. Also, we should have A as the reactant because usually the conversion of reactors is not 100%. So in a more general case, or in most cases, we should have the reactant in the product line. However, in this problem, the statement is saying that the reactant A is completely consumed. So in that case, we can write down in this way without A in the output stream. Then, in this case, do you want to count the 100% consumption of A as an independent restrict? You have used already this condition for drawing this block flow diagram. So you should not count this condition 100 consumption of A when you count the number of equations. So if you did not include B component in the output, so you should not count the condition as an independent restrict. Okay? You have already included that condition into the block flow diagram. The other thing, a mixture is introduced into the unit, and then maybe we have something out of the unit. And also the given information is saying that A component is 10%, B 20%, C 70%. And how many numbers of restricts are there for the stream specification conditions? 3? Do you think 3 is the answer? Because we have 10, 20, 70%. I don't think so. One of the 3 values, like 10, 27, could be calculated from the values of the rest. If you know the information about the composition of A and B, like 10% and 20%, you can calculate the 70% for the C component. So in this case, you have 2 independent restrict or equations, not 3. Let's go to the example for applying the degree of freedom analysis into some processes. Example 2.8, ammonia synthesis. I believe that you are very accustomed to this process, ammonia synthesis process. Nitrogen 3H2 is going to 2 ammonia. So let me check what kind of informations are there. Before reading the problem sentences, so let me write down the block flow diagram. Like in step A in the process calculation. Some system, maybe the system is the reactor for ammonia synthesis. And hydrogen and nitrogen are introduced into the system. And in the output stream, you have 3 compounds, hydrogen, nitrogen, and ammonia. Inside of a system, we have had reactions following this chemical reaction equation in which we have the stoichiometric coefficients. So the first thing we should do is to define the component for the material balance equations. Here is some reactions. So compound could be taken as the component for material balance equations and also known stoichiometry. So from the 3 components for material balance equation, we would have the 3 material balance equations. So I will count those material balance equation for counting the equations or restricts. But let me start with the number of variables or unknowns. The first thing we should count is stream variables. So 2 input and 3 output. So 5. And then the next one is system variables. In the textbook method, reaction is considered as the system variables, not the equations. Actually, can you remember? We have counted the stoichiometric coefficients inside of the chemical reaction equation considered as the relationship or restrict between consumption term and generation term. However, in the textbook method, the chemical reaction equation itself is considered as the system variables. Just follow the textbook as of now, but I'll explain about that in the following slides. So system variables include one reaction but no accumulation. So the total number of system variables is 1. In the textbook method, you don't need to think about accumulation term and the generation term. Instead of them, we have counted the number of chemical reaction equation plus accumulation term. But in this case, there are no accumulation, so we have 1. Then total number of variables or unknowns are 6. Then let's go to find the number of equations or districts. So we have already counted the number of material balance equations from the number of the component for material balance equation, 3. And then the first one is basis. Let's go to the sentences of the problems. The N2 flow rate into the reactor was 150 gram mole per hour. So that is the basis. That's it. And then how about stream composition specification? 1 to 4 for hydrogen to nitrogen. So no. 4 gram more hydrogen per 1 gram more nitrogen. So nitrogen to hydrogen ratio in feed is 1 to 4. This is one stream composition specification. Let's go to the system, and you can find 30% leaves in the reactor outlet stream. So again, 3% of nitrogen fed does not react. Only 70%, 70% of nitrogen is reacted inside of the reactor. So that is the system performance specification. So totally 6 equations or districts are obtained. Then we are very happy because we have 6 unknowns and we have 6 equations, and this problem is well specified. You have just finished the degree of freedom analysis for the ammonia process. Then right now you have known that the degree of freedom of this problem is 0, so we can solve this problem. It's time to calculate the unknown variables by using material balance equations plus several specifications. So it's time to calculate the process variables. So let's do the ABC step presented in the previous subsection 4. As you know, you have the degree of freedom, which is equal to 0, and the 0 value comes from the 6 freedom minus 6 restricts. So I'll follow the ABC step for calculating process variables, and during this calculation also you could find the number of freedom and number of restricts. However, the numbers are a little bit different from the numbers presented in the previous slide. So I'd like to present why there is some difference between the degree of freedom numbers, freedom number and the restrict number in this slide and the same numbers in the previous slide. Okay, let me start with step A. You should define the components of material balance equation, and in this case component is compound, then hydrogen, nitrogen, and also ammonia. So we have 3 compounds as the components for material balance equation. So number of material balance equation would be 3, because the first one is for hydrogen, the second the equation is for nitrogen, and the last equation for ammonia. That is the step A. And then let's go to the step B for defining what is the number of unknowns or what is the number of variables. Unit of unknowns is gram mole per hour because you have got some hint from the basis value like 150 gram mole per hour. And then let me write down the stream variables and then the system variables. In this case, hydrogen and nitrogen are introduced into the reactor as the input number 1. So H1, N1. How about the output? H2, N2, A2. Those 5 guys are belonging to the stream variables. And it's time to go to the system and what kind of terms are available as the system variables. So nitrogen and hydrogen are the reactants. So nitrogen consumption term and hydrogen consumption terms are available as the system variables. How about generation term? Ammonia. There are no ammonia consumption term because ammonia is the product. So ammonia generation terms should be there. Plus accumulation term. However, you don't need to think about the accumulation term because this process is steady state. So accumulation term is 0. So right now we have 3 system variables. So totally we have 1, 2, 3, 4, 5, 6, 7, 8. 8 unknowns or 8 variables are available for this process. So material balance equation 3, unknowns 8. So we need to have 5 more equations. So let me check it. The first candidate for the additional equations or restrict should be basis. So N1, this one, is equal to 150 gram mole per hour. And then also for the input stream specification, then we have known that the hydrogen amount is 4 times nitrogen amount. So we have one more equation. And the other thing is about system performance specification. The conversion is 70% or 30% of the input nitrogen is unreacted. So the consumption amount of nitrogen is 70% of the nitrogen amount in input. Then we have 3 equations. And then 2 more equations could be obtained from the chemical reaction equations. In this chemical reaction equation, you have 3 entities, nitrogen, hydrogen, ammonia. Therefore, you would have 3 different stoichiometric coefficients. You could use 2 of them as the independent relationship. Those stoichiometric coefficients could be interpreted as the relation between reactant or sometimes between product or sometimes between reactant and product. I'd like to use these values 3 and 2. What is the meaning of 3? 3 means hydrogen consumption per nitrogen consumption. It means every the one for one more nitrogen consumed, then you need to have 3 gram more hydrogen consumed. So that is the number 3. The second thing is a generation, I mean ammonia generation per nitrogen consumption is equal to 2. It means for by consuming 1 more of nitrogen, then you could produce 2 more of ammonia, this one. So right now you have additional equation number 2. Of course, you could use the other number like 1 per 1 over, I means 1 nitrogen per 2 ammonia. But this relation could be obtained from those two equations. So you have independent two equations are available from the chemical reaction equations. So right now we have totally 3, 6, 8 equations, and you have 8 unknowns. Then you could solve this problem. So this is my method. I mean, freedom is 8 and restrict are 8. Number of restrict are 8. And then finally, you have the 0 degree of freedom. Okay, so the final results are very similar to the degree of freedom presented in the previous slide by using textbook method. But number of freedom and number of restrict are different between those two slides. So let me compare between those two methods. One is from me, the other from the textbook. So this is the table about the number of variables and number of equations. So let me start with the number of variables. This is a kind of number of unknowns. So stream variables 5, 1, 2, 3, 4, 5 for both methods. However, there are some difference between my method and textbook method in terms of system variables. In the system variables, by using the textbook, you should count the number of reaction. So one number of reaction and accumulation term, no accumulation term. So you have number 1 for the system variables. You don't need to think about the generation term and consumption term. And also you should consider the reaction, chemical reaction equation as the variables. However, in my method, you should think about consumption term and also generation term instead of reaction. So we have 3 system variables. So 1 versus 3. And then the total number of variables or unknowns are different between those two methods. 6 for the textbook method and 8 for my method, Professor Song's method. So there are some difference. For the number of unknowns or variables. Let me go to the number of equations or number of restricts. Material balance equation 3, the same thing, because we have defined the compounds as the components in both methods. So number of material balance equations are the same. Specified flows from the basis 1, the same, and stream composition specification was the nitrogen and hydrogen ratio in feed, so the same one. And specify the system performance specification would be 30% of nitrogen fed does not react. The same. Everything is the same. So the total number of equations are 6 for the previous or textbook method. However, in my method, I need to have two more equations. Those 2 more equations comes from the chemical reaction equations. Again, in the textbook method, the chemical reaction equation is considered as the system variables. However, in my method, I don't take care of the reaction as the system variables. However, I have used the chemical reaction equation for the restrict or number of equations. So in that case, I want to use the stoichiometric coefficients for the relationship between the generation term and also consumption terms. In this case, we could obtain 2 independent equations from two independent stoichiometric coefficients. So the total number of equations are 8 in my case. So anyway, the degree of freedom is the same between the textbook method and my method, because 6 minus 6 is going to 0 or 8 minus 8 is going to 0. So actually the same, but the point of view are a little bit different. So why we should have the same result? So let me focus on the chemical reaction equations. Right now we have this equation. 3 hydrogen is reacted with 1 mole of nitrogen is going to 2 mole of ammonia. The stoichiometric coefficient 3 or 1 or 2 includes information about the accumulation and consumption term. I have said about that in these equations. So in my case, in my method or Song's method, chemical reaction equations are considered as the equations or restrict, actually stoichiometric coefficients. So in this case, we have two restricts, right? I mean, we could find two restricts from this chemical reaction equation. If you have n entity in this chemical reaction equation, then you would have 4 stoichiometric coefficients as the restriction for the process calculation. So let me write down some more generalized number. So right now you have 3 entities, but if you have n entities, then your stoichiometric coefficient would be n minus 1. N minus 1. Okay, that's it. And then, what is the number of accumulation terms and consumption terms in this case? Hydrogen, for the hydrogen, you would have the consumption term. How about nitrogen? You would have the consumption term. How about ammonia? You should have the generation term. So I mean, accumulation terms and consumption terms would be counted as the 3 in this case, because you have 3 entities. So in the case of n entities, you have the number of accumulation and consumption terms should be n, right? So the n-1 is the restriction and n is the freedom. So degree of freedom for the chemical reaction equation is n minus 1 is equal to plus 1 here. So it is right, and it is easier to understand. I mean, my method would be easier for understanding because we'll follow the one by one step for finding the number of equations or number of the unknowns. However, resultantly, chemical reaction equation indicates degree of freedom, which is number 1. So in the textbook method, without this kind of detailed consideration, the the textbook method consider the chemical reaction equations as unknowns, just plus one. I means number of chemical reaction equations are the number of unknowns. In this case, you don't need to think about accumulation term and the consumption terms. So actually, those two approaches are going to the same result. So before the process calculation, you could use the textbook method for estimating the degree of freedom. However, for the process calculation, you will follow my method. It would be better. Here is the second example for degree of freedom analysis. Example 2.9, light from a chip. Maybe you could remember these equations for the process calculation. Um, so let's go to the block flow diagram, and here is the reactor, MOCVD reactor, and 3-methyl gallium, this one, T4 3-methyl gallium is reacted with ammonia, A4 ammonia. In the presence of inert gas is introduced into the MOCVD reactor. Inside of this reactor, you can find alumina chip, and by using these chemical reaction equations, gallium nitride is electrodeposited on the alumina chip inside of the reactor. So this gallium nitride is accumulated inside of the reactor, and you can find only methane with inert gas in the output stream. So let me check several specifications. In this problem statement, you can find 1-to-1 molar ratio between reactants like T and A. Also, we cannot find any T and A and G in the output stream. It means 100% conversion between 1-to-1 molar ratio of the reactants. So even if we have two specifications, the first specification can be considered as the stream composition specification, and the other thing, this one, only methane in output stream, could be considered as the system performance specification. But we cannot use those two specification or restrict as the restrict. I means those two conditions are not involved as the restrict when you are calculating the degree of freedom, because right now you have used those two conditions already when you are drawing the block flow diagram. If you want to use this specification later, you should write down like that, and you should think about T T in the upstream and also A in the upstream. However, right now we don't need to think about those two things, because 1-to-1 reaction is going to zero the reactants in the upstream. Okay, so again, we will not use those two conditions in the when you are counting the number of equations you are restrict. Okay, anyway, you should write down or draw the block flow diagram for the counting the number of variables and also equations. Like step A in the process calculation, here is the block flow diagram, and you should define what is the component for the material balance equation. Of course, here is the well-balanced chemical reaction equation. So it is better to use the compounds as the component. So Ta with I, Ta, this is T and A with I is going to the system. Then you could find some M methane with the inert gas I. That's it. And do we have the accumulation term? Because in the textbook method, you will count the number of the generation term. So, no, accumulation term. However, you don't need to think about generation and consumption term, right? In the textbook method. So, let me focus on the accumulation term. What is accumulated? That is gallium nitride, which is electrodeposited on the alumina chip. How about the chemical reaction equation? We have one. Okay, anyway, from the component number of components, we could expect five number of material balance equation. TAI M no TAIGM. Five. Five component means five number of material balance equation. Anyway, keep it in your mind. And then let me start with the number of unknowns or variables. How many stream variables do you have in this block flow diagram? 3 for input and 2 for output. You don't need to think about T and A in the output stream because we have already used those two conditions. So 1, 2, 3, 4, 5. 5 stream variables. And the other thing, how many system variables we have according to the textbook method. Again, you don't need to think about generation and consumption term. Only thing you need to think about is accumulation term, right? One plus one more equation. So system variables, number of system variables are 2. Then totally 7 unknowns are there in this problem. And let's go to the equation. Some specified flows may be basis, so I cannot find the basis here. So 0. And stream composition specification, of course, we have 1-to-1 molar ratio for the input. However, we have already used this condition for during the while we have drawn the block flow diagram. So it should be 0. How about system performance specification? We have had like 100% conversion or no methane there. No, the only methane in the up there. But we used already these conditions. So system performance specification, which is independent, is 0. So only thing we can use is the number of material balance equation coming from the number of component for material balance equation. So totally 5. Number of variables or number of unknowns is 7 minus number of equations or restrictions are 5 is equal to 2. It means this problem is under specified. So what kind of opportunity do we have for this calculation? The first thing is basis. There are no basis. It means you should determine the size of the this MOCVD reactor. So you should define a basis, right? So after defining the basis, you do have number 1 specified flows or something. So right now 5 is going to 6. And one more things. So we don't need to think about the inert gases which was presented in the previous the same example. Current cannot affect the reaction and cannot affect the G accumulation, any the other terms. So I would like to kill this the inert gas term. So let me kill this one and this one. It means the stream variables is not 5, then right now 3. And then 3 plus 2 is going to 5. Okay. Also, you should kill the one equation for the material balance equation, because one of the material balance equation is made for the inert gas. So it is going to number 4. And then it is going to number 5. So after defining the basis, and then you would have DO, 0 DOF like 5 minus 5 without considering inert gas. Then you could calculate the all terms related to T and A and G and M. That's it. So you can solve this problem after fixing the basis. Example 2.10, battery acid production. Actually, you have met the same or similar example before. Your job is to design a mixer, so the system would be a mixer, to produce 200 kilogram per day of battery acid. The mixer will operate at steady state, so you don't need to think about the accumulation term as the system variables. The battery acid product must contain 18.68% sulfuric acid in water. Raw materials available include a concentrated sulfuric acid solution at 77% sulfuric acid in water. That is the first input. And a dilute acid solution that contains 4.5 weight% sulfuric acid. This is the second input. And pure water, third input. Is this problem completely specified? So this problem is the thing of degree of freedom analysis. So as the step 1, let me draw the block flow diagram or input-output flow diagram. Here is a mixer and 3 streams are introduced. And the product stream is going out of the mixer. So let me take the compounds as the components for the material balance equation. In this case, S stands for pure sulfuric acid, 100% sulfuric acid, I mean. And the other thing is pure water. So the first 2 input streams would have S and W. So maybe let me write down S1, W1, S2, W2. And in the third input stream, you would have a pure water. Also, in the output stream, you have a mixture of sulfuric acid and water. So we have 2 components for material balance equation, like sulfuric acid S and water W. There are no reaction. So number of materials equation would be 2 because we have 2 components for material balance equation. Then let's go to count the number of variables or unknowns. The first one is stream variables. 1, 2, 3, 4, 5, 6, 7. 7. And how about system variables? there are no accumulation because it is the steady state, and there are no generation term. Also, there are no consumption terms because we don't have any reactions. So you can say you would have zero system variables because no reaction and no accumulation by the textbook method. And then total number of unknowns is 7. The next one is the number of equations or restricts or information. So I have said material balance equations are 2 from the number of components here. And then the first one you will count is the basis, specified flows. So 200 kilogram per day product is our target, and also it can be considered as the basis of this process. So number 1. And then the next one is about stream composition specification. You have the information about the concentration of the first input flow. It was the most concentrated concentration, 77 weight percent. The next one is 4.5 weight percent. And for the upstream, you have your target actually 18.6 weight percent sulfuric acid. So the number of the stream composition specification is 3. Maybe you can think about the concentration of water. But in this case, we have assumed that we have only water in the third stream. So 100% water for the third input stream is not counted as the new equation or independent equation. So please check this sentence. The percent water in each stream is not independent. So you don't need to think about this one, this one, this one. Because after you have the information about the sulfuric acid composition, then you could calculate the content of water for each stream. Okay, so you have just finished the number of the stream composition specification, and next one is system performance specification. There are no information for this problem, so 0. And I have said we have 2 material balance equations. So total number of equations would be 6. Degree of freedom is equal to 7 freedom minus 6 restrictions. So you have number 1 for your degree of freedom. So you can say this problem is under specified. I mean you have one more freedom. So you could fix one more restrict. It is a kind of the chance to optimize the solution to minimize cost. For example, you can fix the flow rate of pure water. Example 2.11. Eat your greens is a catchphrase of this problem. Salad greens are washed to remove dirt, bugs, and other debris before being packaged for sale. A facility processes 1,500 16-ounce packages of greens per day. It is a kind of basis for your product. The fresh picked greens contain 1 pound debris per 12-pound greens. A kind of composition, I think. The salad greens are mixed with 150 gallon water per day and washed. Another basis, then spun to separate the dirt water from the greens. The process removes 99.9% of the debris and all of the wash water from the salad greens. So this is the first system performance specification. We are thinking about the separator. And the other thing is 100% water is removed from salad greens. This is the second system performance specification. The washed greens are sent for packaging. The dirty water is dumped to a river. The plant is limited by environmental constraints to dumping a maximum of 4 barrels of water per day at a maximum debris content of 1.5 volume percent. So this is another the basis or specified flow rate. So we have three the basis candidates. Too many bases. Also, the other one is the concentration specification for the product. And the question is this problem completely specified? So of course, this problem is the degree of freedom thing. So let me write down the block flow diagram or input-output flow diagram. Actually, we have two units. The first one is mixer, and the second one is separator. This separator is a kind of spinner. So the first one is mixer or washer, and the second one is separator or spinner. So a mixture of salad and debris are introduced into the washer, plus clean water is also introduced into the same unit. And then after mixing together, then those mixture is transferred into the spinner. And then finally you have two output stream. The first one is the cleaner salad. Of course, this clean salad also includes the debris, but the amount of debris is smaller than before. Also in the second output stream, you have water containing debris. So, okay, here is one important point. In this case, I didn't say about water in the first output stream. In more general cases, you should include water in the first output stream. Let me write down water here. However, I want to use one of the conditions from the problem statement to simplify these problems. Here, all of the water from the salad greens are removed. So I have used this condition when I have drawn this picture or this block flow diagram. So I have removed this water. Okay, so we have already used this condition. All of the 100% of wash water is removed from the salad greens. So you should not use this condition when you count the number of equations or number of restricts, because we don't have water in the upstream of the block flow diagram. So in this case, component is the salad greens, shortly S, and water, shortly W, and debris, shortly D. So then we have finished the very fresh block flow diagram. And then let me take the system, including mixer and separator. So this is the system. You don't need to think about the stream between the washer and spinner. What is the number of material balance equations? That is 3, because we have 3 different components for material balance equation. And then let me count the number of unknowns or variables. The first one is stream variables, and let me count them. 1, 2, 3, 4, 5, 6, 7. You don't need to think about the stream between the mixer and the separator, because I have taken those two units as the one single system. How about system variables? You should count the reaction and accumulation. However, this is the steady state, so you don't need to have accumulation term, and there are no reaction because we are thinking about just mixer and separator. There are no reactor. So total number of unknowns is 7. The second thing we will count is the number of equations, or the restrict. We have already counted the number of material balance equation, which is 3, number 3. And let's go to the first the entity for this table. The first thing is always basis. In many cases, you have only one basis. However, in this case, we have 3 different bases. 1,500 bags salad per day for output stream, and 150 gallon washy water per day is introduced into the system for the second input stream, and 4 better dirty water dumped to river per day. This is the specification for this output stream, the second output stream to the river. Anyway, we have 3 for these specified flows. And then let's go to the stream. What kind of stream composition specifications we have? The first one comes from here, the 1 pound debris to 12 pound salad greens. That is the composition. Also, the other thing is environmental constraint. That was the 1.5% debris in the dirty water can be allowed to be dumped to river. This specification is for the second output. So we have 2 stream composition specifications. How about this system performance specification? 99.9% removal of debris could be done inside of the system. That is the first system performance specification. Actually, we have had one more thing. 100% washy water is removed from the process. However, I have said we cannot count this condition because we have already used this condition by removing water in the upstream. So you don't need to think about the second condition for the system performance specification, which was 100% removal of water. So the number of system performance specifications is number 1. Then total number of the equations or restrictions would be 9. Degree of freedom is equal to 7 from the unknowns minus 9 from the equations or restrictions. So minus 2. It means we have more amount of restricts than the number of unknowns, minus 2. So over specified. I means 2 more number restricts is over specified. So we cannot solve this problem. I mean, you should remove 2 of the conditions that are given to you. So here is some idea when you are removing one of the conditions. Solve the problem without environmental constraints. Okay, so you don't need to think about this one, 4 barrels of water per day at a maximum debris content of 1.5 volume percent, and then calculate the whole process. Then you could evaluate the value of the amount of wastewater plus the waste concentration. Then check if the solution complies the constraints. The values you have obtained from your calculation is smaller than those two uh, environmental constraints, then you are very safe. You don't need to think about the environmental constraints. However, if you have higher values of the wastewater amount or wastewater concentration, then you should change one of the other conditions. For example, amount of water or amount of the salad or something like that. That is the examples for the subchapter 5, which is about degree of freedom analysis. Here is the new subchapter 6, calculation for multiple process units. And let me start with an example, the title of which is Toxin Accumulation. An immunotoxin, or IT, is a drug designed to kill cancer cells. An IT is constructed from two proteins. One protein, usually an antibody, specifically targets cancer cells and leaves healthy cells alone, while the second protein kills the cell once it is inside. Anyway, it is a kind of introduction about the immunotoxin. An experimental IT immunotoxin is internalized into cancer cells at a rate of 185,000 molecules per minute. So it is a kind of the basis. Inside of the cell, all the IT first enters a compartment called an endosome. It is a kind of entrance which acts like a splitter. 97% of the IT that enters the endosome is spit back out of the cell. So here is the schematic diagram, and this is the cell, and this cell could be considered as the system, and immunotoxin is introduced into the cell. The first organ of the cell is endosome to get the immunotoxin. So I have said about endosome in this problem statement. 97% of the IT that enters the endosome is spit back out of the cell. So spit back out of the cell. And the amount of this immunotoxin is the 97% of the introduction. So this value is about the system performance specification. Much of the rest is sent to a compartment called a lysosome. So this is the lysosome, where it is degraded into harmless byproducts at a degradation rate of 5500 molecules per minute. This is another system performance specification of lysosome. So this lysosome could be considered as the reactor because the immunotoxin introduced into this reactor is going to some harmful product. And then this harmful product is going out of the cells. So lysosome is a kind of the reactor. Anything remaining moves to another compartment this way, called the cytosol, and where it accumulates. So a cytosol plays a function of a kind of storage tank. So some immunotoxin is accumulated inside of cytosol. It is estimated that 500 IT molecules must accumulate inside the cell. So this is the capacity of the cytosol to accumulate the the immunotoxin molecules before it will be killed. And how long will that take? That is the question. So right now we have already drawn a block flow diagram. Endosome, cytosol, lysosome, and immunotoxin is introduced into the endosome, and some portion of immunotoxin is going out of the endosome, and also the degradation product is going out of the cell from the lysosome. So in this case, I'd like to take this whole process as a single system. So system is entire cell, and endosome like splitter, lysosome functions like a reactor, and cytosol could be considered as a storage tank. And in this case, component is the compound, and also we will consider only IT, immunotoxin. We don't have any chemical reaction, stoichiometry. So right now we have only one component, which is IT. So number of materials equations is just one. And then let's go to step B. Define number of unknowns, and then I will follow my method instead of the textbook method in this example. IT in and IT out. Also, inside of the cell, some portion of IT in is consumed, and then which will be converted to some degradation product. Also, some portion of IT is accumulated in the cytosol. So this is our block flow diagram, and then number of unknowns are 4. So IT in, IT out. Also IT consumptions as the system variables, and also IT accumulation. So we have 4 variables in terms of IT. But we have just only one material balance equations, so we need to have 3 restrict or equations. So let me try to find some information which could be used as the restrict or equations. The first one is basis. IT in is 185,000 molecules per minute. Also, we could find 2 system performance specification. One of them is for the endosome. Right, endosome. The other thing is about the lysosome. So 97% of input is going out of the cell. Also, here is the degradation speed, like 5500 molecules per minute. So we have 3 more additional information. Then the total number of unknowns is 4, and also total number of equations or restricts 4. So you could calculate the systems. After the calculation, you would have the information about IT consumption, IT accumulation, and also IT output. So what was the final question? It is estimated that 500 IT molecules must accumulate inside the cell. That is the capacity of the storage tank before it will be killed. Then question is, how long will that take? So IT accumulation rate is 50 molecules per minute. So after 10 minutes, we would have 500 molecules in the cytosol, and then the cells will be killed. So my answer is 10 minutes before the cell will be killed. Okay, then let's go to the second example for the multiple units for calculation. Actually, in the previous example, we have 3 different units, but we have taken a whole system as the single, a whole entire process as the single system. So in that case, we didn't have any information about the variables between the units. In this example, we'll calculate all of them. So for example, here we have very many units in this process: mixer, reactor, separator, mixer, reactor. So we have 5 units. Of course, like in the previous example, we'll take a whole entire process as the single system. In that case, we could calculate the true input and true output. But in this case, we cannot calculate the variables between the units. For example, here's the muconic acid between separator and the mixer 2. When we take the whole process as one single system, we cannot calculate the variable of muconic acid between separator and mixer 2. So in that case, you should take each unit as the system. So I'll show you this kind of cases in this example. In this process, we'll make the adipic acid from glucose. So let me follow the sentences. And actually, this process is given to you in the end of the chapter 1. A preliminary block flow diagram for production of 12,000 kilogram per hour of adipic acid from glucose based on the technology described in chapter 1's case study is shown in this picture. So this is the basis, and air, glucose, water plus E. coli is introduced into the whole process, and then finally we can get adipic acid. E. coli is a kind of a bacteria, looks like this one. So the full name is Escherichia coli. You have it. You have them in your lower intestine. Available raw materials are air here to be 21 mole percent oxygen and the remainder nitrogen. So this is the input composition specification. The other thing is glucose solution at 10 milligram per milliliter in hour. So another composition. And hydrogen. Hydrogen is introduced into the system at mixer 2. So hydrogen. Those things, this one and this one, are raw materials. So let me follow this a series of units. So the first reactants are introduced into the mixer 1, and then that mixture is going to the reactor 1. The reactor 1 is a kind of fermenter, and inside of the fermenter, this E. coli, this bacteria, digest glucose and oxygen. Then finally, this bacteria would produce muconic acid. This muconic acid is finally converted to the final product, adipic acid. Anyway, let me go back to the reactor 1. So in this reactor, we have a chemical reaction equation with stoichiometric coefficient. 100% conversion was assumed. Then, after the reactor 1 or fermenter, nitrogen and carbon dioxide, muconic acid as the intermediate, and water, and more biomass of E. coli there. And the next unit is separator. By using this separator, we have separated the muconic acid from nitrogen carbon dioxide and also E. coli in water. Then the muconic acid is mixed with hydrogen gases in the mixer 2. Muconic acid, the mixture of those two things are introduced into the reactor 2, and then muconic acid is hydrogenated, and then finally to the adipic acid. So you can find the adipic acid at the final output stream. Also in this reactor 2, we have assumed 100% conversion. Then we will calculate every unknown variables, for example, the meconic acid between separator and mixer 2 or something like that, by using the process calculation. This is the main theme of this subchapter 6 about the multiple units for calculation. So at the very first trial, I'd like to take the whole system, whole unit, or entire process as a single unit. So something like that. I have a big box, and it's a kind of input-output flow diagram. So in this case, let me count the number of material balance equation and unknowns and or more restrict. Here, before calculation, let me try to calculate the degree of freedom. So following the textbook method. So, but anyway, before counting something, it is better to draw the block flow diagram. This is the block flow diagram. This is a system which is the entire process. And then oxygen, nitrogen, actually air, is introduced into the system. Also, glucose solution, G stands for glucose, W stands for water, are introduced into the system. One more things. Hydrogen is going to the mixer too. So anyway, the hydrogen is another input. Also, we have three different output stream, and this is the adipic acid for A. The other thing is nitrogen, carbon dioxide from here. The other thing is E. coli solution in water here. So I don't want to think about the E. coli mass here because it is not considered as the variable in this case. So right now we have 1, 2, 3, 4, 5. 5 input variables and 1, 2, 3, 4. 4 output variables. And we have actually two reactions. One reaction for reaction 1 and the second reaction is for reactor 2. However, after we have taken entire process as the single system, then what we need is the overall reactions. This is the overall chemical reaction equation after by combining those two reactions. One is for reactor 1 and one is reactor 2. So we have only one overall reaction equation. So one reaction, and this process is following the steady state process, so no accumulation. So the total number of variables or unknowns is 10. 5 plus 4 plus 1 reaction is going to 10. Then let me count the restrict or equations. Let me start with the material balance equation. How many components are there? So in this case, I have taken the compound as the component for material balance equation. So oxygen, nitrogen, glucose, water, hydrogen, carbon dioxide, and adipic acid from this block flow diagram or input-output flow diagram. So 7 components are there, so 7 material balance equations. And 2 input specification are there. we know the concentration of glucose means glucose moles and per water moles. So one input specification. The other thing is the ratio, molar ratio of oxygen to nitrogen in air. It is given to you. So totally two input specification. How about output? We have the basis. So totally 10 districts are obtained. So 10 minus 10 is equal to 0. Then we can solve the problem after you have taken the whole process as the single system. Okay, let me follow my method for estimating the degree of freedom. Textbook method is better when you want to calculate the degree of freedom number before the process calculation. However, if you want to calculate the process variables, all of them, then it is better to follow my method for estimating degree of freedom. Anyway, before calculation, I mean before process calculation, textbook method is better. However, if you want to calculate everything, my method is better. Anything is okay in terms of degree of freedom calculation. So in my case, 5 input, the same. 4 output, the same. But in my cases, I will count every each terms for the system. We have 3 reactants, oxygen and glucose and hydrogen. So oxygen, glucose, hydrogen consumption terms are available for the system variables. The other thing, adipic acid is generated plus CO2 and water. So those 3 guys could be considered as the generation terms for the system variables. No accumulation term like in the textbook method. So I have counted 6 system variables here and plus 0 accumulation terms. So totally 15 variables or unknowns are available for this problem. And then let's go to the restrict or equations. 7 material balance equation, the same. And 2 input specification, the same. 1 output is the same. However, in my case, in my method, you should think about the stoichiometric coefficients. So in the overall chemical reaction equation, you have 1, 2, 3, 4, 5, 6 entities. It means you have 6 stoichiometric coefficients are available. It means n-1 relationships could be obtained for relating between consumption and generation terms. So you have 5 equations. So 5 stoichiometric coefficient. So again, the number of unknowns are like 15, and also the total number of restrict or equations are 15. So 15 minus 15 is equal to 0. You can solve this problem. Let me check again. What makes the difference between my method and textbook method? In my method, I have unknowns or variables and also equations which are related to the reaction. 6 system variables which are related to the reactions, and also 5 stoichiometric coefficients are also closely related to the chemical reaction equation. The difference between those 2 things are 1. So in the textbook method, when you meet the chemical reaction equation, you should consider just 1 unknown or variables. So 6 minus 5 is going to 1. So simply for obtaining the degree of freedom, the textbook method is better. However, when do you want to calculate every variables, then my method is better. But anyway, from the viewpoint of calculation of degree of freedom, my method and textbook method is going to the same value. In this case, 10 minus 10 equal to 0 and 15 minus 15 is equal to 0. So anyway, I have solved the problem about the adipic acid production process from glucose, and in this case I have calculated only pure input variables and pure output variables because I have taken the whole entire process as the single system. However, we need to calculate a lot of variables existing between the units. So in this case here, between mixer 1 and reactor 1, here reactor 1 and separator. This one, between separator and mixer 2, and this one, mixer 2 and reactor 2. So in that case, you will take a single unit as the single systems. So let me try to calculate the degree of freedom of each unit for the mixer 1. So for input and for output, right? For I, for O, and zero reaction for the mixer 1, so zero reaction and zero accumulation. There is the variables or unknowns. How about the restrict or equations? So we have O and GW, O and GW. We have 4 components, so 4 material balance equation. And the specified things was the composition of air and the composition of glucose solution. So we have 2 input information. So 8 minus 6 is going to 2. The degree of freedom of mixer 1 is 2. How about the following process, reactor 1? 4 input and 4 output variables, and we have 1 chemical reaction equation for the reactor 1. So 1 reaction plus 0 accumulation. So totally 9 unknowns. And how about material balance equations? O and G, W and the same, C, M, W the same. So 6 components could be used for the material balance equations. So 6 material balance equations. We don't have any more information about that. So 9 minus 6 is going to 3. And let's go to the third unit. 4 input and 4 output, 0 reaction because this is the separator, and 0 accumulation because it is steady state. And then let's go to the restrict, and we have NCMW. So 4 components for 4 material balance equations. So 8 minus 4 is going to 4. Mixer 2. 2 input unknowns or variables and 2 output variables, and no reaction, chemical reaction equation and no accumulation. And we have only 2 components, HM, so 2 material balance equations. So 4 minus 2 is going to 2. How about the reactor 2? 2 input, 1 output variables, and 1 chemical reaction equation for the reactor 2, no accumulation term. So for freedom, and HMA, we have 3 compounds as components for material balance equation. So 3 material balance equation, and the output stream the flow rate was given to you. That was the basis. So 1 output. So 4 minus 4 is going to 0. Then it means for the reactor 2, we could calculate all variables including H10, M10, and A6. Then let's go to the mixer 2. Right now we have known these values. From the viewpoint of mixer 2, this is the output. From the viewpoint of reactor 2, this is the input. Anyway, from the calculation about the reactor 2, we have got new information for the output stream of mixer 2. So we should add two more additional information. Then 4 minus 4 is going to 0. So you can solve all the values of the variables of mixer 2. Okay, then right now we know this value, and with this value you cannot solve the problems about the separator, because totally 8 and 4 mass balance plus one more additional information, then it is very the degree of freedom is just 3. But however, from the previous slide, we have calculated the overall input and overall output. So when the entire process was taken as the system, we have calculated this value and also this value and this value, and actually this was given to you from the problem statement. So after calculation about the mixer 2, we know this one. So four additional the information are given to you right now. So 4 minus 4 is going to 0. So you can solve all problems about this separator. Then let's go to the reactor 1. The degree of freedom is 3. And right now you know the information about NCMW for the stream 8. So the degree of freedom is right now -1, right? And then it means over specified. Maybe one of the added specification is redundant to other conditions. So in that case, we can solve the problem. Then right now we have 4 values, and also actually from the entire system calculation, we actually have already know the input variables. So you don't need to do additional calculation about the mixer 1, because you can have this value from the reactor 1 calculation, and also this value comes from the entire process calculation. Then you could solve all unknown values about this process. This is the table for the final answer. So detailed calculation is you can do the detailed calculation by yourself. This is the summary table for the example 2.15, adipic acid production from the glucose. You are a chemical engineer, and your boss asked you to synthesize or design a process. So what can you do it for making the process? Here is the procedure to place units in order for a process. The starting point is reactor. So draw a reactor, and then place a mixer before the reactor. Your reactor have probably multiple streams of inputs, because you have multiple raw materials for a reaction. So it is better to mix all together just before the reactor. Then only one stream is introduced into the reactor. The third one is separator before the mixer. Usually your raw materials would have some impurities. It would be better to remove the impurities before introducing your raw materials into the mixer and then going to the reactor. So the third one is separator before mixer, actually before the reactor. The fourth one is another separator after reactor. Reactor have usually a single output streams, sometimes multiple output streams, and in the output streams you would have, of course, desired product plus unreacted reactant plus byproduct. We need to separate your desired product from the others, including side products plus reactant. So you need to have separator after reactor. The fifth one is splitter, which is placed after the separator after the reactor. Add splitters if the quantity of a stream is greater than needed in the downstream process unit. That is the fifth unit you should place in your process. The sixth one, or the last one, is mixer for recycle. If unreacted reactants leave the reactor and are separated from the product streams, then add a mixer upstream of the reactor to mix these recycled reactants with fresh reactor feed. So the last one is mixer. Here is the memorization tips. Let me take the very first letter for each unit. R, M, S, here R, M, S, and S, 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 and mix. RMS could be read as the root mean square. So root mean square here. And then you have the product of S and S. So S square. So root mean square of the S square is going to just S. The first character of my family name. So you can memorize this order. It's like this one. Songs, coffee mix, because the first five things is the simplified into S after root mean square of the S square. Then the final one is mixer, actually mixer. So songs, coffee mix stands for RMSSS mix. So again, reactor first, mixer and separator, another separator, and splitter if you need to have, and then finally mixer. Okay, here is a kind of an example, and then let's place a series of units in order for making a process. This is the process for making the adipic acid from glucose. Sketch a block flow diagram for production of adipic acid from glucose given the reaction pathway. We have two chemical reaction equation. Maybe you need to have two different reactors. This is the glucose, and oxygen is going to an intermediate which is a muconic acid, and then going to carbon dioxide and water. This is a kind of digestion process or combustion process by a bacteria, E. coli. This is food, and then for digesting the food, we need to have oxygen like a human being, and then the product with carbon dioxide and water like combustion. This muconic acid as an intermediate is hydrogenated into the final desired product, adipic acid. In this case, oxygen, air is the source of oxygen, so we would have the nitrogen additionally. Glucose is purchased as a dry product, but is dissolved in water on site before being fed to the process. So, okay, let me make a process, or let me draw a block flow diagram from this process from glucose to finally adipic acid. The starting point is always reactor. So let me start with the first reaction. Then here is the reactor 1. It is a kind of fermenter. And then into this reactor 1, air as a mixture of oxygen and nitrogen, dry glucose, and pure water plus bacteria, E. coli, are introduced into the reactor 1. And then in the final output stream would have nitrogen because nitrogen is unreacted, and carbon dioxide from the reaction 1, and muconic acid from reaction 1, and water from reaction 1, and okay, muconic acid, this one, not this one, and more E. coli. This is the first reactor 1. So here is the reactor 1. And several things are introduced into the reactor. So it would be better to mix all together in a single mixture. So you need to have mixer 1. So this mixer 1 is placed just before the reactor 1. Okay, mixer 1 have the multiple input stream, like air, the first stream, glucose, the second stream, water, third, and E. coli, the fourth stream. It's going to the mixer 1 and all together mixed totally. And then after the mixer 1, you should have the only one single mixture. That is the air, glucose, water, E. coli. The compounds are the same, but you should have only one upstream after the mixer. So this one stream is going to the reactor 1. So we have this one. Let's go to the second reaction or reactor. So what we know is hydrogen and muconic acid required for the reaction 2. And then final product is adipic acid. That is the starting point for the second reaction. And then of course, we need to have the mixer before the reactor 2 because we have two different compounds. So hydrogen and muconic acid are introduced into the mixer 2, and then we have a single mixture of hydrogen and muconic acid. This single output stream from the mixer 2 is going to the reactor 2. So you have this one. Okay. Then it's time to connect reactor 1 and mixer 2. As the product of the reactor 1 or in the product stream from the reactor 1, you have four compounds. Muconic acid, that is the desired product, and muconic acid should be introduced into the mixer 2. How about the other things? Nitrogen, carbon dioxide, water. It would be better to separate the muconic acid from nitrogen and carbon dioxide and water before going to the mixer 2. So we need to have the separator. So separator have one input stream each coming from the reactor 1, but as the output streams we have three different streams. Of course, the muconic acid should be introduced into the mixer 2 from the separator after separation. Nitrogen and carbon dioxide is a kind of gaseous phase, so it's going out from the top of the separator. And the other E. coli solution of water is going out of the separator into the bottom stream. That is the whole process for the glucose to adipic acid process. And then right now you have several multiple units in order for the process. You have covered all content of chapter 2. about process. Then let me finalize this chapter with a case study. The title of this case study is Evolution of Greener Process. Roundup is a popular biodegradable non-selective herbicide. Glyphosate is the active ingredient. When sprayed on foliage, glyphosate is absorbed by the plant and blocks the action of a specific enzyme, which prevents the plant from making essential amino acids. Plants wither and die within a week of being sprayed. This is a kind of the introduction. A key intermediate in the synthesis of glyphosate is disodium imidodiacetate, disida. In the conventional process, disida is produced by reaction of formaldehyde, ammonia, and hydrogen cyanide. A new process is proposed, which uses safer and more environmentally benign chemicals. In this process, diethanolamine, shortly DEA, this is diethanolamine. This is the amine, and we have two ethanol here and here. Go back to the sentence. So diethanolamine, or DEA, is synthesized from ethylene, oxygen, and ammonia in a two-step reaction pathway. In the first chemical reaction equation, ethylene is oxidized to ethylene oxide. Ethylene plus oxygen is going to ethylene oxide. And then this ethylene oxide, which could be considered as the intermediate, is reacted with ammonia, and finally we could obtain DEA, diethanolamine. So we have two reactions. Finally, DEA reacts with sodium hydroxide to make disida, but we will focus on the generation of DEA in this problem. A very preliminary economic analysis looks favorable, so we'd like to pursue some ideas for designing this new process. So let's go to the solution. So right now we should design the process and based on the block flow diagram. How can we build up the block flow diagram? Let's follow the method of Song's coffee mix, or RMS-SS mix. As you know, the starting point is the reactor. So we should have two reactors, and the first reactor is about conversion of ethylene plus oxygen into ethylene oxide. In the second reaction, we will make the desired product DEA from the intermediate ethylene oxide plus additional raw material ammonia. So right now we have two blocks separately to each other that they are reactors. And then it's time to add mixers and then connect the mixers and reactors. So we have the first reactor, then you should place the mixer 1 in front of the reactor 1. In the same way, we need to have mixer 2 in front of reactor 2. So ethylene and oxygen are introduced into the mixer 1, then the mixture of those two things are introduced into reactor 1. Then if you have ethylene oxide from reactor 1, which is fed into the mixer 2 with ammonia, and then the mixture of those things are going to the reactor 2. Finally, we will have the DEA as the desired product. So this step is about M, the second one. In this block flow diagram, we have assumed that all ethylene and oxygen is converted to ethylene oxide, or or ethylene oxide and ammonia is going to DEA 100%. However, it is very difficult to obtain the 100% conversion reactors. So let's go to the third one. We have some limitation of the reactors. So there are some assumptions here. For the reaction 1, all the oxygen, but 25% of the ethylene is converted to ethylene oxide. So oxygen conversion is 100%. However, ethylene conversion is limited to 25%. And reaction 2. This reaction must be carried out in the absolute absence of oxygen. Probably this reaction 2 is very sensitive to oxygen content. So in that case, we need to have a separator between reactor 1 and mixer 2. Here is the role of separator 1. I have said some portion of ethylene is converted to ethylene oxide. So in the output stream of reactor 1, you would have the ethylene and sometimes oxygen plus ethylene oxide. Of course, I have assumed that the whole oxygen is totally consumed in the reactor 1. So for calculation, you don't need to think about the existence of oxygen before the reactor 2. Anyway, you should consider the very tiny amount of oxygen would be there. Sometimes not. So I have placed the separator 1 before the mixer 2. The role of separator 1 is separating the ethylene oxide from ethylene or trace oxygen. I mean, even if you did not calculate the amount of oxygen, but you should think about the trace oxygen. So one of the role of separator 1 is to remove oxygen from ethylene oxide. Anyway, in the first output stream of separator 1, it should be ethylene oxide, and in the other stream, you would have the ethylene plus trace oxygen. So in this case, we would have the only ethylene oxide for mixer 2 and then reactor 2. So this is the third step of build up the process, then this one. So RMS. And here is the additional information. Even if we have used the oxygen in the previous slide, but it would be better to use the air as the oxygen source. So I'd like to introduce air into mixer 1. And all of the oxygen is consumed in reactor 1 and the nitrogen would pass through. So in the output stream of reactor 1, you have one more the entity of molecules, that is the nitrogen, as well as ethylene and ethylene oxide. While still, we should think about a tiny amount of oxygen. So we have one more role of separator 1. Separator 1 should separate the ethylene oxide from the mixture of ethylene and nitrogen and oxygen. So it is going out of the separator 1. So this is the block flow diagram. E stands for ethylene and N stands for nitrogen. O stands for oxygen. The same thing, and ethylene oxide is here, EO, and the final product DEA is abbreviated as the D, and A stands for ammonia. And we have two reactions for two reactors respectively. Okay, let me do some process calculation. Of course, for getting the values of every unit, you need to take each unit as the system. But before going to each calculation, I'd like to show you the entire process as a single system. In this case, we have a big black box as the entire process, and ethylene, nitrogen, oxygen, and ammonia are introduced as the raw material for this process. The product is ethylene and nitrogen, and also DEA as the desired product. Also, we have only one overall reactions. Actually, in the problems, you have met the two different chemical reactions. However, we are thinking about the entire process. In this case, you should build up the overall reactions. For example, this is the first reaction, then the product of the first reaction was the intermediate, and this intermediate is reacted with ammonia is going to DEA. So the overall reaction is like that after killing this intermediate and this intermediate. So 2 ethylene plus oxygen plus ammonia is going to DEA as the desired product. Let me do the process calculation with step A, B, and C. In the step A, we'll count the number of material balance equations. System, the entire process. And I'd like to take the components for material balance equation as the compounds. So what is the compounds here? Ethylene, nitrogen, oxygen, ammonia, and DEA. So we have 5 components for the material balance equations. So it means 5 material balance equations are available. Let me do the degree of freedom analysis or DOF analysis following the textbook method because we didn't calculate yet. So first, here's the freedoms. So 4 input variables, so 4 input, and 3 output variables, 3 O output, and only 1 reaction, overall reaction. So 8 freedoms are available. And then let me check the restrict. We know the ratio between nitrogen and oxygen, 79 to 21. So 1 input restrict, and also we have the basis. We know the value about the production rate of DEA. Let me say that is the 1000 kilogram more DEA per hour. So 1 output restrict, and 25% of the ethylene is consumed. That is the system performance specification. So 1 system restrict and 5 mass balance equation from this value. So 8 restrict. So 8 minus 8 is equal to 0. So we could solve this problem. Let's go to the B step. Step B, to count the number of unknowns. The first thing is basis, 1000 kilogram DEA per hour. So from the hint of the basis, we'll use the kilogram mole per hour as the unit. And let me check another freedoms. So in my method, we have 4 input variables and 3 output variables. Those 2 things are very same to the textbook method, and plus we need to have system variables. In my method, I count all terms included in the system. In this case, ethylene consumption term oxygen consumption term, and nitrogen consumption term, and the DEA generation term. So we have 4 system variables, then 11 freedoms there. So we have 11 freedom or unknowns, but we have only 5 material balance equations. So we should find 6 more restricts or informations. Let's go to the step C for finding additional restricts. So basis 1000. This is the restrict. And stream composition, right? And system variable is only 25% of ethylene is reacted with other reactant. So you can find 75% of the raw material ethylene is remaining in the output stream. That is the E4. Actually, E5. Yep. So we have 3, and 3 more equations are required, and you can find the 3 more information from the stoichiometric coefficient. Here is the overall equation, and 4 entities are there. It means 4 stoichiometric coefficients are there. So 3 relationship between consumption terms and generation terms are available. In my case, ethylene consumption per the DEA generation term is equal to 2. Oxygen consumption per DEA generation is equal to 1. And then ammonia consumption per DEA generation is 1. So we have 3 more stoichiometric equations. So then degree of freedom of this system following my method is equal to 11 unknowns minus 5 materials balance equation plus additional restrict 6, so 0. Then you can solve this problem. By using those restricts and after setting up the material balance equation, then you can solve this problem. So this is the answer, and please do the calculation by yourself. Okay, so in the previous slide, we have calculated some variables for the entire process, but not for each unit. So these values comes from the entire process. Again, 7 are stream variables, 1 chemical reactions, and then they are freedom, and restrict is also 8. So degree of freedom is 0. Then you can calculate this one, this one, this one, and this one, this one, this one. So right now we have those values in our hands. Then let me check the degree of freedom of each unit. Let me start with mixer 1. So stream variables 1, 2, 3 plus 1, 2, 3, 6. No chemical reaction for the mixer. And then specified flows 0. We don't have any information about that. And stream composition 1, because we know the ratio between nitrogen and oxygen in air. And system performance, nothing. Material balance equation, let me check the number of components. ENO, ENO. So 3 different compounds are there. So material balance is 3. So the total number of variables or unknowns are 6, and restrict is 4. 3 plus 1, 4. So degree of freedom for the mixer 1 is 2. Let's go to the reactor 1, and we have 6 stream variables, and we have 1 chemical reactions. You don't need to think about the accumulation term for the system variables, because those processes are operating under the steady state. Flow specification, nothing. Stream composition, nothing. System performance is 1, because 25% of ethylene is reacted. That is the system performance specification. How about material balance equations? we have 1, 2, 3, the same, 4. 4 compounds are there, so 4 material balances are available. So total number of unknowns are 7 and the total number of restricts are 5, so degree of freedom of reactor 1 is 2. The third one, separator 1. 1, 1, 2, 3, 4, 5, 6. 6 stream variables with no chemical reaction and the no specified flows, no stream composition, no system performances, and material balance. Let me count the number of the compounds. ENEO, ENEO. So we have 3 different compounds are there. So material balance equations are 3. So total 6, total freedom 6 minus total restrict 3. So degree of freedom for separator 1 is 3. Then mixer 2. We have 1, 2, 3, 4. 4 stream variables, no chemical reaction, and we no restriction about the flows, the other thing, but we need to think about the material balance equations. So how many compounds are there? EO, AEO. So 2 different compounds are there. So 2 material balance equation. Degree of freedom is 4 minus 2 is going to 2. The reactor 2. Stream variables 1, 2, 3, 3. And chemical reaction 1. And flows 1. The values of D is known. That is the basis. 1000 kilogram mole DEA per hour. So 1 specified flows. That is the basis. That is the basis, and no stream composition, no system performances, and material balance equation. We have 3 compounds, so 3 material balance equation. Then total number of freedom is 4, and the total number of restricts is 4, so 0. Then it means you can solve this problem about the reactor 2. Let me sum all of the variables and equations. How about stream variables? 6 plus 6 plus 6 is equal to 18, 12, 2, 22, and 25. So total stream variables is 25, but it is not true because some stream variables were counted redundantly. For example, this one, EO is the stream variables, and this is the input stream for the mixer 2. At the same time, this is the output stream from the separator 1. So when you sum those values along the stream variable laws, then you will count some variables redundantly. So in that case, you should count the variables from the pictures directly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Do not sum values along the law of stream variables. Some variables are counted redundantly. However, in the other cases, like chemical reactions, flows, or something like that, you can sum the laws. So we have 2 reactions. The sum is 2, and flows only 1, and the stream composition only 1, system performances only 1, and material balance 3 plus 4 plus 3 plus 2 plus 3, 15. So the total number of variables are 18, and the total number of restricts are 15 plus 1 plus 1 plus 1, 18. So anyway, you can solve the problem. Also, you have already known several values after the process calculation about the entire process. This one, this one, this one, this one, this one, this one, this one. Then let me go back to the mixer 1. We have two freedoms there. But you can find those two freedoms from the values obtained from the entire process calculation. ENO is known. So actually the ratio of NO is known and also counted as the restrict. So we could give the two more restrict like E and N into the mixer 1. So degree of freedom was 2, and right now we have two more information from the overall calculation, so you can solve this problem. So about the mixer 1. Then the degree of freedom of reactor 1 was 2. However, we have just calculated the variables about the mixer 1. So those three values are known right now. So three more restrictions are there. Then we could satisfy the degree of freedom at 2. We have more information. So you can solve this problem. Then let's go to separator 1, which have the degree of freedom at 3. And after the reactor 1 calculation, you have 3 information. So with the 3 more information from R1, then you can solve the problem, because 3 minus 3 is going to 0 as the degree of freedom for this separator 1. Then how about mixer 2? Degree of freedom 2, mixer 2. And after the calculation about separator 1, we have one more additional information as the input variable for the mixer 2. But we have degree of freedom at 2. So 2 minus 1 is equal to 1. We need to have one more information. So we have failed to use the additional information from separator 1. So let me start from reactor 2, because the degree of freedom of reactor 2 was 0. So we could solve the problem. After the calculation about reactor 2, we know those two values, A and EO, as the output stream of the mixer 2. So two more information from R2, then you could satisfy the degree of freedom of mixer 2 at 2. So finally 0. Then you can solve the variables about mixer 2. That's it. And then we could solve all variables right now. So this is the result. And then let me check some values. How about this one? Stream 9 about diethanol amine, or DEA, was the 1000 kilogram mole per hour. That was the basis. It was already known value. And then let me check the amount of ethylene. In the stream 1 here, we have fed 8000 kilogram more ethylene per hour into the system. Now let me check the stream 5, this one. From the separator 1, we are discarding the ethylene and nitrogen. The amount of ethylene is right now 6000 kilogram more per hour. How wasteful. I mean, 75% of ethylene feed is not used for the reactions. Just the 75% of the amount of ethylene is just discarded. So we'd like to save those discarded amount of ethylene. In that case, we should think about recycling of the discarded ethylene from separator 1 into the mixer 1. So it's time to redesign of our processes. So again, it's time for redesigning by using the recyclers. So recycle this stream, about 6000 kilogram more per hour of ethylene is fed back to the mixer 1. maybe with ethylene you could have nitrogen plus trace oxygen into mixer 1. One more consideration. Put separator 2 to separate unreacted ethylene from the N2. So in the first case, we have just fed back the mixture of ethylene, nitrogen, and trace oxygen into the mixer 1. But I'd like to introduce very pure ethylene gases into the mixer 1. In that case, you need to have the separator along the recycle stream. So right now we have separator 2. This separator 2 placement is belonging to the third entity of RMS-SS mix. So right now the mixture of separator 1 is going to the separator 2, and in the separator 2 we have separated the ethylene from the nitrogen and the other trace gases. Then it's time to calculate the variables in the recycled process or redesigned process. So let me check the overall or entire process. I have drawn big box like that, and we have ENO, I mean ethylene, nitrogen, and oxygen, and nitrogen is going out of the separator 2, and ammonia are introduced into the mixer 2, but into the big black box, and the final product is D. So we have 1, 2, 3, 4, 5, 6 stream variables and 1 chemical reactions. Of course, we should think about the overall chemical reaction equations instead of 2 separate equations, because we are not thinking about the intermediate in the entire process. So 7th freedom, and then what is the restrict? The flows, the basis for D, and then composition for the L, and material balance equations. Let me check the number of compounds. ENO, the same. AD, ENOAD, 5 compounds are there, so we would have 5 material balances. So 1 plus 1 plus 5 is 7. 7 minus 7 is 0, so we can solve this problem. Then after the calculation, we would know the value about ethylene, nitrogen, oxygen, and nitrogen, ammonia, and DEA. One more point. Actually, we have had this system performance specification for the reactor 1. That is the only 25% of ethylene is consumed inside of the reactor 1. But we cannot use this system performance specification for this entire process. Of course, you could use this restrict you can use this restrict for the reactor 1 calculation. So you should remove this one. You know, this E value, the value of the ethylene amount, is not related to directly related to the system performance specification, because some ethylene amount is recycled to the reactor 1, so the input amount of ethylene gases are changing from the previous system without recycles. So in that case, we cannot use that system performance specification. Anyway, after we make this black box and several calculations, we know those values 1, 2, 3, 4, 5, 6 from the entire process. Then let me change the system. So I'll take mixer 1 and reactor 1 as the system. So in that case, we have E and O. E and N and O are introduced. Also, another E is introduced from the separator 2, and the output is ethylene, nitrogen, ethylene oxide. So let me check the degree of freedom. 1, 2, 3, 4, 5, 6, 7. 7 stream variables and only one chemical reactions for reactor 1. And then no flow specified and stream composition 1, which is the composition of air. And then system performance. In this case, you could use the system performance here because this value, the ethylene amount in the output stream, is related to that system performance specification. So 1. And how about material balance equation? How many compounds are there? E and O, same, ethylene oxide. So we have 4 compounds are there. So 4 material balance equation. Then total number number of stream of variables. No. Total number of variables or unknowns are 8. 7 plus chemical reaction 1. So 8 is going to there. And then number of equation is 1, 2 plus 4, 6. So degree of freedom of the system including mixer 1 and reactor 1 is 2. But we have 2 more information which was calculated from the entire process. 2 more, like the value of E and N. So total degree of freedom is going to 0 after you considered the calculated values of variables from the overall process. So right now you can calculate the other variables. So right now you know the values about this one and this one. Then let's go to each unit. The mixer 1, reactor 1, separator 2, mixer 2, reactor 2. I have calculated the degree of freedom for each unit like that. And then it's time to calculate about the mixer 1. So we have 3 freedoms are there. And from the system including mixer 1 plus reactor 1, we could find 1 more information. This one, right? And then 2 more information could be obtained from the overall process, E and N. So right now we have 3 more additional information. So we could satisfy the degree of freedom as 3. So 3 minus 3 is going to 0, then you can solve this problem. Let's go to the reactor 1, 2 degree of freedom. Then from the calculation about the mixer 1, you have the values about the variables, those things, which are the input stream for the reactor 1. So 3 more information was fixed. Then it means we have more information to satisfy the freedom of 2. Then you could calculate it. Then next one, separator 1. And right now we have 3 more additional information which was calculated from the mixer 1 plus reactor 1 system. Then 3 from mixer 1 plus R1, so 0, then you can solve this problem. Separator 2, and then after the calculation about separator 1, we know those 2 values. So by using the 2 values from the separator 1, you could solve this problem because the degree of freedom of separator 2 was 2. So 2 minus 2 is going to 0. How about the mixer 2? And degree of freedom of the mixer 2 was 2. And from the separator 1, we could obtain the 1 more additional information. So 2 minus 1 is equal to 1. 1 more freedom remaining. So we cannot solve this problem by using the information about the separator. So let me go to the reactor 2 first, because the degree of freedom of reactor 2 was 0. So we know the values related to reactor 2 is known. So D, of course, which is the basis, and also EO and A in the stream 8 was known. So by using those two more information, you can solve the problem, because the mixer 2 had the degree of freedom at 2. So 2 minus 2 is going to 0. Then you will have all variable values. This is the list of the equations. Then you can use those equations and material balance equations. Then you can solve the problems. Do it by yourself. One more redesigning. We have used the separators in the previous uh, the case. However, separator is too expensive usually. So let me replace separator 2 with splitter 1. So only 80% of the feed to the splitter is recycled to the mixer 1. So 100% mixture of ethylene and nitrogen gases is introduced into the splitter, and 20% of them is going out of the splitter, actually going out of the system. And then the 80% of ethylene nitrogen mixture is introduced into the mixer 1. Then also you could calculate um, the system variables about the system, very similar to the previous example. Um, Let me check the amount of ethylene fed to the process. In the original setup or process, we have used 8,000 kilogram mole per hour. But right now, after we have used the recyclers, we successfully reduced the amount of ethylene gas into the 3,200 kilogram mole per hour. So it means by using the recyclers, we have saved our cost for the feedstock. Okay, that is the chapter. That was the chapter 2, and your homework is there.